Vipin Kumar from University of Cologne in Germany. So Vipin did his PhD from Physical Research Laboratory in 2022, and he worked mostly on FOSC instrument for the PRL optical telescope. So currently he is involved in the development of a Warm Calibration Unit that will be utilized for the very extreme European telescope, which is 39 meter. Is this the diameter, 39?
Yes.
When it is going to come? Like,
maybe in 2029.
it is too big.
I'm
Okay.
audible like so.
So his research interests are optical IR instrumentation and study of cool and low mass stars. So yeah, you can start.
Yeah, maybe you don't heard from me today about MBROS. It's instrumentation talk today. Okay. So thanks, Jagdish, for your kind introduction. Okay. So good afternoon, everyone. In today's presentation, I will be talking about my work, which I have involved in last 7 to 8 years. And mostly I worked on like instrumentation, optical IR instrumentation for astronomical objects to do the astronomical science. And I will be talking about in this presentation about two topics. One is the current involvement, which I am working in University of Cologne from Warm Calibration Unit, WCU, which is being developed for METIS instrument, which is mid-infrared imager and spectrograph. And it is for basically to calibrate the extremely large telescope. And also in later part of the talk, I will be talking about some FOSC instrumentation, which I have worked in my PhD actually. And those instruments are basically for MIRO, which is Mount Abu Infrared Observatory. So let's start from like my plan of the talk. So first I will give a quick introduction to my work, what kind of instrumentation I'm doing, and what kind of science I am involved in. And then I will move to the first part of my talk, where I will discuss what is ELT, what is the status of the ELT, what is METIS, and then I will jump to the Warm Calibration Unit, its requirement and its design concept. And then I will move to its MAIT phase, which is basically manufacturing, assembly, integration, and testing phase, which is now going on. And then FOSC instrument. Here I will be talking about 3 different instruments. One is FOSC, which is already on the telescope. Another instrument is FOSC EP, which is a shell polarimeter. It's basically moderate resolution shell polarimeter, which does spectropolarimetry. And then I will talk about some kind of prototyping we were doing there. The name of this instrument is Protopole. Now it's fully fledged instrument. And then I will summarize my talk, just giving a brief overview. What are the contributions, all of these works I was doing. So let's start. Okay. Basically, why do you need instrument? Because anyway, one can say that we have telescope, then what? We have telescope, but of course you need instrument to do like science. So in the end, you have telescope, but in the end, what you need from the telescope is your science results, right? There is chain between telescope and science results. So from the telescope, you will get the light. Then you need instrument to analyze that light. After the instrument, you will have some raw data, not the science ready data. So you need actually the pipeline, data reduction pipeline, which basically convert your raw data to science ready data. And then you need some tools to analyze your science ready data. And then you have the science results. After that, you have like many kind of instrumentation people are doing, like imaging, spectroscopy, interferometry, polarimetry, IFUs, chronography, all those kind of work is going on. There are also subsystems like AO and calibration unit, which are not delivering the science data, but they are actually helping to improve the quality of the data. Then you have like space-based observatory, you have ground-based observatory, and you have huge range of wavelength. So in the end, what I wanted to show you, like what kind of work I am doing out of all these areas. So I'm doing like for ground-based observatory, I'm doing optical IR wavelength domain. And I'm doing like imaging, spectroscopy, and colorimetry kind of instrument. Next is, of course, in the end, you need some science result. So what kind of science I'm interested in? So I basically work on M dwarfs. These are the like cool objects, smaller in size, and also mass is also less. If you see the HR diagram, it will work or not. Slowly. Okay. So if you see the HR diagram, on y-axis you have luminosity, on axis you have temperature profile. So starting from high temperature to low temperature in this side, and M dwarfs somewhere lie here. It means like you have low luminosity of the objects and you also have low temperature. So these kind of objects I'm working on. Why these objects are important for me, as I'm also involved in instrumentation. So for me, it's important because they are good number you can find in the sky anytime, like throughout the year, you can find those objects in the sky. And they also have lots of spectral features. So if you are dealing with the instrumentation for spectroscopy and so, it means you need some objects which show basically the spectral features. Then you also have magnitude range, like starting from bright 5, 6, 7 magnitude, and then faint like 14, 15, 16, 17 magnitude. So basically these things helps to characterize your instrument. Also astrophysical significance, there's because they are like low mass, which means they burn slowly. So they have like good galactic history if you observe them. And then you also have great significance for exoplanet searches. So people are working like detection of exoplanet around the M dwarfs, and there are many more significance, of course. So till now, you know what kind of instrumentation I am involved in and what kind of object I'm interested in. Now I'm moving the first part of the talk where I will discuss this WCU, Warm Calibration Unit, on METIS. So let's start from ELT. And of course, one can say this is the world's biggest eye on the sky because it has like 39-meter huge diameter primary mirror, which is this one. This is no single dish, of course. There are like 798 segments are there, and each one of them is 1.4 meter in diameter. So these are the specification of different mirrors. So M1 is this one, which has like 39-meter diameter. M2 is somewhere here. You can see this is the secondary mirror, and the size of this is around 4 meter, exactly 4.25 meter. And then after this, like wavefront height hits here, then it goes there, and then somewhere here you can see M3, and then M4 is somewhere here, M5 is somewhere here. So after M4, it will actually hit to M4, and then after M4, it will focus your light somewhere here where the instruments are present. So there are two Naismith platform, one is here, another one is here, and instruments are there, and you will be surprised like when you observe the starlight, everything basically rotate. It means this telescope structure, this Naismith platform structure, and the instrument as well. And the whole weight of this thing is around 6,100, not 6,100, it's like 6,000 ton rotates while observation. So there are first generation instrument. One is METIS, which I'm working on. Another one is Mikado, which works basically with this Morpheo instrument. And third one is Harmony, which works in different wavelength domain. I will be for this 1.4 meter. So METIS I'm working on. Mikado is actually doing in optical domain, and Harmony is also doing in optical domain, but it is dedicated for IFUs. So telescope first slide, as people always ask. So 2029 they planned. Now they are pushing to work like in 2029 they can achieve, but it most likely 2030 may have the first light. And between METIS and Mikado, there is always like chasing each other. Sometimes METIS is forward, sometimes Mikado is forward. So let's see which one out of at least these two instruments would be the first light instrument. So now talking about the METIS baseline design. So first thing, like this is the render of METIS. where you have this cryostat where all the science instruments are inside and cool temperature, and we are actually outside. So this is the system which we are working on. This is the warm calibration, and that's why we call it warm calibration, because this is not inside the cryostat, we are outside the cryostat at room temperature. So specification of METIS, it works between 2.9 to 13.5 micron. And the spectral resolution for different modes, like it works, it does basically imaging. LSS is long slit spectroscopy. It does like a low resolution spectroscopy, coronography, and IFU spectroscopy. Resolution, if we talk about for low resolution, they are working between 400 to 4,000 roughly, exactly 3,800. And high resolution, they basically built with IFU, and the resolution of this IFU unit is around 100,000. And it works basically in L, M, and band only. Other specification for field of view, for imaging field of view, L and M band, they have separate detector, which use a sky of 10.5 arc second by 10.5 arc second. And these are the for N band images, little bit larger. And for IFU spectroscopies, 0.9 arc second by 0.6 arc second, which is really tiny field of view. Mass, weight, you can see the number. This is huge structure. Now I'm moving to like what are the science drivers actually, because if you are spending that much effort, money, time, everything, of course you should have some good science application also. So people like when started this proposal for the METIS instrument, they initially started like when they are fixing the technical requirement, they initially started with these two objects, circumstellar disk and exoplanet. But of course, as time goes, people come with different idea that, okay, that can also be done, that can also be done. And nowadays, you have really huge science cases in the in this report. If you see, there are a lot of science cases, around 100-page report. So people are working like on circumstellar disk, history of the solar system, exoplanet, of course, AGN, star formation regions, and evolved stars. Of course, I will be not talking about everything, but at least to give an idea that how the specification of any instrument set up by science cases, I will little bit discuss about exoplanet, which of course not my field, but to give glimpse of idea that how those specifications are set up. So let's say take one specific example that you want to study, let's say super warm Earth, which you cannot do with the existing facility nowadays. Even with VLT or like bigger telescope, you cannot do those. You cannot study super warm Earth. What does it mean by super warm Earth? Super Earth is basically, that's the size. It is little bit around this 1 to 2 Earth radius. And warm, like Earth temperature, it's around 300 Kelvin. We are talking about here 500 to 700 Kelvin. And if this planet is around the M dwarf, let's say within 10 parsec, then to study those kind of object, what do you need actually from the instrumentation people? What do you need is resolution, which can detect to those tiny planets around the M dwarf, which is basically few milliarc second. And if you know people who observe with at least like Davis Thal or Mount Abu, our seeing limited is around 1 arc second, right? Here we are talking about actually milli-arc second, 1,000 of 1 arc second. And what you also need, like if you want to resolve a planet around the M dwarf, you need to have like some kind of contrast imaging, which can block the light of the actual star, and then you can see the planet. So the contrast you need at this wavelength, you need around 10⁻⁻⁶. It means you can only see the planet which have this kind of contrast in this wavelength. Also, if you want to do the spectroscopy, like say, for example, atmospheric characterization or so, you need 100,000 resolution to do the atmospheric characterization. These requirement, if you convert to the specification of the instrument, few milliarc second we are talking about, so you need 40-meter class of telescope, which actually converts, if you have 40-meter class telescope, then you can hit actually the diffraction limited if you calculate that number. And of course, if you calculate that number, it will be few milliarc second, but how you will actually achieve this milli-arc-second level, because you know, if you are on the ground, you have the turbulence in the atmosphere. So to achieve, we need AO. So at least those two specifications are clear. We need 40-meter class telescope. We need adaptive system. Next, this contrast, how you can achieve? You need coronagraph, which can do actually high contrast imaging. And the last one, of course, you need a spectrograph, high resolution spectrograph with IFU. Why IFU? Because first you need to actually remove your the main star thing, which you need actually full field of thing. That's why we need actually IFU, and then you put your spectrograph after that thing. So at least you can see that you have one science goal, and then you have like list of parameters in terms of instrumentation that what you need actually. Then to have some idea, this is the curve like from VLT NACO instrument. Till now, what we can achieve, you can only, like the least number I'm talking about. So you can start from this, like which is around 10 power minus 1, which is 0.1, 0.2, 0.3. So till now, what we can do actually around 0.3 arc-second separation is there. If then only we can resolve those planets, then we can only detect those planets. And contrast, if we talk about, we are hitting till here only, like 10 power minus 3 around, which means like 1,000 times. If your star is 1,000 times more than the planet, then you can only do. If it is more than 1,000, it is like 10 power 5 or so, then you cannot do those things. If you talk about these two curves, those are basically from METIS. One is without HCI, another one is with HCI. So this red one is actually with the coronagraph. So what you can achieve now with this whole setup, 10 power minus 2, which is 0.02. It means like you can actually detect the planets which have the separation of 0.02 arc-second, which is 20 milli-arc-second. So if you have a system which are really away from your star, within 2 AU or so, within that distance, you can actually do those kind of science here. One example from the simulation, this is the example I could find in the report, that if you use this METIS HCI simulation for L band and you have the coronography system and you want to see how it can work. So this is one example. This is the Jupiter size of planet, and there is a star. And this is the known system from RV method, and the known separation around 0.12 arc-second. So you can see like the separation is around within 20 milli-arc-second. So this is 120 milli-arc-second. And then you can easily resolve, because the contrast you can achieve 10 power minus 6. So that kind of science we are sure that we can do with the METIS instrument. Now let's move. Okay, we know that those kind of science can be done with the instrument. Now I will take a little bit time here that, yeah. Because it's expel on the detector, the light. So that's why you need to have like system. You have to constrain your how much bright that a star can be, where you actually can separate. Because if it expel basically, yes. Yes. We are talking about parsec. Yes. No, I'm not. Yes. Yes. Now the point is low. It's really close. Like we are talking about, like even with the height as a 10-meter class, you are not able to see planet, which is very tiny. We are talking about like few milli-arc-second. So that's why it is very tiny. And if you even block that star, you can have some expel. And that's why, if you may heard, like if you are working in instrumentation, like there is inner working angle for the HCI, right? That tells actually that even if you have a resolution, you cannot go to that limit actually. So those parameters are there. Mhm. Yes. Yes. No, it's not mostly like I just present that science case. There, yeah, yeah. Mm-hmm. 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 Yeah. Mm-hmm. Yeah, one thing is, I'm not really expert of those things, but what I read actually, that they have some molecular bands. They have those really fine structure lines there, which can characterize your atmosphere of the planet. It is not like the reflected spectra. So what you are talking about is basically, I think, reflected spectra. Here we are not talking about the, yes, yeah. Mm-hmm. Yes. Uh, that I can tell you, like I can check what are those refined structure that you can do with those resolution. But okay, uh-huh. Okay, okay, okay. Yeah, I think. Mm-hmm. Mm, at least this is not true actually. That if you go to like direct thermal spectrum from the exoplanet, I think it's different, right? Slightly different. So if I have those spectra, I can show you and maybe we can discuss those things as well. Okay, so this is the like block diagram of the instrument to have just some idea, okay, how this is working. And at least it is also good to see the internal part of the instrument, that how actually those components are working. So just to give an overview, I will not go one by one. So there are like 4 different modules of this instrument. This is we called CFO, which is common for optics. The function of this common for optics is to tell the other systems that what field you are choosing and in which orientation actually you are using. So there are 2 units. One is here, which is derotator, which can actually rotate your field. You don't need to rotate the whole instrument. You just rotate the inner part, this module, and you can rotate the field. Here you have like chopper kind of thing. So you know in infrared, actually you want to deter the, you have to dithering, right? Dithering means like you have to little bit change the telescope orientation, then you will observe again. And then you will use those 2 images during your data direction. So here you don't need to do that thing from the telescope side. You just move this chopper and you can actually change the field as well. So this is the function of CFO. After that, when everything done, it comes somewhere here. Before that, you have also here, like this is the light we are talking about in L, M, and N band. We have this beam splitter here, which actually reflect J and H band light to the SCAO module. What is SCAO module? Single conjugate adaptive system. So it uses that J and H band light, and then after sensing the wavefront, it actually send the commands to the main telescope, and then it will correct your wavefront error. After that, it comes here, and then from here, you can split your light either to LMS, which is the IF unit, and you can also you can remove this fold mirror, and then you can send your light to these 2 subsystems, which is like imager in LM N band, and the another imager in N band. So this is the whole idea of the instrument. If you have any question, little bit, you can ask. Mm-hmm. Yes. In optical. No, that's not really true actually, because we know this thing by theory that if you are correcting like you are using J at H, like infrared light, and if you are using this optical light, the infrared is better. So that's why I'm using J and okay, so this is the block diagram. Now I'm moving to our subsystem, which is the Warm Calibration Unit. And again, like in general, why calibration are important? You know that they can provide the wavelength solutions, because when you get the image from the detector, it's basically pixel versus intensity. Then you have to convert somehow from pixel to wavelength, and then you need some kind of source which can do that thing. Another point is like remove instrument induced signature, which means you have to remove your response of the instrument from the spectra or imaging. And then sometimes people also use your calibration unit to support the AIT activities. What I mean AIT activities, basically, when you are assembling the things, it will actually help and provide the source. Specifically, WCU, what are the requirements? Again, I will take some time here. So one by one, so let's say we are talking about diffraction limited imaging. What are the requirements from that side? Let's say we are talking about PSF calibration. We have to do calibration for the PSF. For PSF calibration, it is well established that you need at least 95% of Israel ratio. And if you can convert this number to wavefront error, it comes around 109 nanometer. It means like if you're designing your warm calibration unit, you should not go beyond this number. And this is really, really tight number. You cannot feel it maybe, but I can tell you in this way. So 109 nanometer you have to achieve. And our warm calibration unit size is around 3 meter. And we have to put the optics on this range, like 3 meter apart. And the tolerances, we have to achieve this number. The tolerances are around plus minus 50 micron also. So this is really tight number, and it is constraining our optical design. Another factor is ensure correct PSF modeling. It means we have to provide the ELT lag beam. It means F number you have to replicate and pupil you have to replicate. Another parameter is detector gain variation we have to calibrate, which means you need some kind of flatness. And the requirement is around 0.3% over the detector field of view. These first and second can be achieved by working on the optical design and mask. And the third one you can achieve by choosing your suitable broadband source, which is blackbody we are using, and integrating sphere. You have to design the integrating sphere as well. Another factor is from the IFU spectroscopy, what people expecting from us, that we have to provide wavelength calibration accuracy of 1/10 of the pixel. If you convert that number to the wavelength domain, it is around 10 picometer, even not in nanometer. 10 picometer is 10 to the power minus 12. It's really fine thing. Another requirement is if you go to around this region, 4.68 to 4.78, the telluric emission coming from the sky is very poor. So you cannot find many lines. That's why it is also required that in your calibration unit, you provide these lines in your calibration unit. So you need to provide some kind of sources which can be tuned within this wavelength range. This can be chosen by suitable monochromatic sources. And the last one, AIT activities, which means we have to see the different focal planes and pupil planes inside the METIS system, see those things, and then align each subsystem. So basically, this is coming like you need to have some kind of imaging optics in the WCU, which can see the different subsystem and can tell you, okay, now those two subsystems are aligned. So these are the whole specification of WCU, what you need. Now things are set up, you know what to do, and then move to the next thing, the full design. I'm not showing the block diagram because it's the replication. So I can tell you here actually that we have one integrating sphere here, which is, you can say, the source. But of course, you need different source. So we have 3 laser sources which can be injected by the fiber. You have black body source here, and you put basically the mask wheel here to change the flux level as well. Then after that, you have some mask wheel here so that you can tune your pinhole according to the requirement. And then you have some optics here which basically reflect those things. And then some sort of optics is there. And then again, this is the flat mirror. It basically goes down. We have another flat mirror here. And then it injects the light into the cryostat subsystem. So the field of view is around 27 arc second, 29 actually, sorry. I will come to the next slide. It's 29 arcsecond. So the size I mentioned here because it's important that what kind of size we are talking about. It's around 3 meter by 2.4 meter. And the mass is around 1.1 ton. It's not easy to handle those things actually. So you also have to think how to deal those kind of mass when you are doing the assembly. These are some parameter field of view as you asked. It's 29 arcsecond. Wavelength range, this for METIS, this for our AIV optics, which we have to use during the alignment phase. Operating temperature of the black body. Okay. So the operating temperature while you are operating this thing is around 0 to 15, which is room temperature kind of thing. And sources which we are using for breadboard source, we are using black body, which is somewhere there. And we are using 3 laser source actually for the monochromatic purposes. One is helium neon, simple 3.39 micron. And this is tunable Q shell we are using, which I just talked about, that we need to tune some wavelengths during this wavelength range. And one in the end, which is around 5.26 micron. So these sources we have in the WCU. Next, it's optical design. Of course, if you have the things like the constraint are ready, then you can constraint your design in terms of optimization, like to achieve the performance, also in terms of what you can manufacture. So these are the parameters. I'm not going through all the parameters, but what you should notice here is this, the wavefront error. It's 109, the same number. The nominal design is 42 nanometer. Of course, 42 nanometer seems less compared to 109, but when you add up everything, it's around of that order. I can tell you those numbers. So this is the wavefront error, just a map to see what kind of wavefront error we are achieving. And in relay optics, we are using 4 flat mirrors. It's basically here, 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 and here. And 3 curved mirror, which are basically this one, and this one. Wavefront error, 42 nanometer is nominal, but of course, once you do the tolerance analysis, because you cannot put everything ideally, right? So we have some tolerances on tilting, positioning, everything. And then after tolerance analysis, we are 90% confident that we can actually achieve 89 nanometer wavefront error. And then if you include everything, the surface foam error from the mirrors, mounting deformation, everything, we are achieving around 100 nanometer, which is close within the limit what we are constraining ourselves. This is one of the error. It would be good if I place my hand or something so that you know. We are talking about 281 millimeter diameter, which is like this much big. So this is the optical design. Now let's talk about the sources. As I already told you, this is the black body what we are using. Monochromatic sources. This is one of the helium neon laser we are using. We are characterizing actually in the lab. Another is tunable QCL. This we are actually characterizing now. And the last one is the last 5.26 micron laser that we have already characterized. So in this setup, you can see laser source is actually here. Then you have somewhere beam splitter here. It basically sends light, 50% light to there, which actually will go to WCU. But now we are putting some sensors so that you can check the power. And here you can use the coupling lens, and then you can send your light to the wave meter, from where you can know, okay, what wavelength we are talking about. And for achieving that particular wavelength, we are using like current input for the laser and the temperature setting. And actually between, if you play with the current and temperature, you can achieve the wavelength wherever you want with the accuracy of 10 picometer. It's infrared optics in Germany. Yeah. No, it's all wavelength. So 600, 700, it also gives, but we use that light only for AIV optics. It also gives like 3 micron to 15 microns. It actually gives to 20 micron, which is sufficient. Now, the flat mirror we have, those are very big. Then we have to think about the assembly process, that how you will assemble those things. So actually what we are using, I will not go into really detail, but what we are using is plunger-based concept. What does it mean, plunger-based concept? When temperature changes, during the transportation we are talking about, the operation range is really like 0 to 15, but you have to transport as well. and the temperature range is really huge, starting from -33 degrees Celsius to like 85 degrees Celsius. In that range, what can happen if we direct fix this mirror to the mount, it can crack actually during those temperature ranges because of the stress on the mirror. So we are using actually plungers. So you hold optics from one surface, and on the other surface, you use actually plunger. When it wants to expand, it can expand. And then when the temperature is normal, it will go back to the previous position. So this is the concept, how we are mounting those things. We have another concept, like because we are talking about 3-meter range, when the temperature changes, actually the mirror can change its position as well. So what we are using, like this spring-based concept, if temperature changes, either it will move inward or outward, but the vertex of the mirror should be at the same position. So this is another concept we are using in the assembly process. Then this is one example that how we are assembling the things. This is one mirror, and then you put some cap to protect its surface, and then you start mounting this mirror to the actual assembly, and this is how it looks like in the lab. And as of now, we are characterizing the deformation using a wavefront like interferometer, that if there is an effect on the surface as well. So 0 0 is really best thing in terms of CT effect. The CT is really 0. Yeah, but that's also expensive. Really? Fuse silica. Maybe. But people are really using like everywhere in METIS. So maybe that's why we are also using short, like everywhere in the other subsystem also, they are using short thing. And that's maybe the reason that I use. But yeah, I can. It's aluminum. Yeah. Yes. Invar is again more expensive and more weight actually. Yeah. True. I can tell you this thing. So we have aluminum. As I said, this CT is very high actually. Invar has really 0, like not 0, but really less number. But those things are really not affecting the assembly thing. As I told you, if temperature changes, it will just change the spring thing. It will just more force on the spring. The spring changes, but the location will be the same. So there is no effect. So why we need to go to like Invar, which basically create like more mass and more expensive those things. So aluminum is working fine. Yeah. Yeah. So basically here, like for the curved mirror, we are using aluminum. For the 0 door, we are using for the flat mirror only. Yeah. So there are 2 combinations. Flat mirrors are 0 door, and the curved mirror, the spherical mirrors are the aluminum one. So this whole assembly is aluminum. It's gold coating. Yeah. Okay. So in this thing, it's a very simple thing that you don't want to touch your curved mirror surface, because we saw in during the Crowdline analysis, if you touch your surface directly while mounting, it will deform your surface a lot, create aberration, create wavefront error more, and then you're out of your constraint. So we are using this concept. Okay, you have the mirror here, but you actually mount with this surface, only those 2 surfaces. So that's working fine. Challenges I already told you. This is like the parts what we have already in the lab that we are doing the assembly. These are the companies where we got those parts. Okay, now I moved to like some of the AIV optics design. What I was telling you, that we need to have some optics inside the WCU which can actually image different pupil planes and focal planes. So these are the 2 designs to use when you want to image your focal planes in the METIS subsystems. You can use this design, and if you want to use you want to image your pupil, then we have this design. This was optimized like last year, and then you have really problems while optimizing the pupil planes, because if you see the pupil inside the WCU or METIS, it was really tilted, and if you want to image tilted things with your optics, it will be like really aberrations are there. Somehow we managed to optimize this, These are some parameters like what are the requirements. Just two numbers to keep in mind. The RMS diameter, what we are achieving after tolerance analysis is like 12.1. The requirement was in terms of, yeah, it's 15 micron, this number. So we are within that thing. Also here, the after tolerance analysis, we have this 0.3% of pupil diameter, but the requirement was between those two numbers, 0.1, 0.5%. So we are good with the design as well as the performance wise. This is again the same concept we are using for the lens assembly also, like you have plunger from top and the side. So we don't need to worry about the temperature effects. And then this is how you will then assemble each lens cell to the barrel. So we have 2 barrels, 5 cells, combined everything, check your system in the lab, and then it's fully characterized. This is one example I'm showing, like what we are doing now in the lab, that we have already tried to put the lens in the cell, and what we are using the portable CM as of now to check this concept actually is working or not. So it was working well. Now, I'm also the part of the work that we have to actually align everything. So you need to make a plan, the AIV plan actually. So for the AIV thing, what we are using, these two tools, one is FIS by interferometer, another one is portable CM. How we will use? So we'll use actually this concept. So on one side, you can put your interferometer. On another side, you can put your actually test surface or your mirror, which you want to align. And then in between, you can put the 2 targets, which are just crosshairs. And then you see the picture. So it's like this. You fit the things and you can actually tell, okay, you are this much far away or not. And then try to bring like at 0, like you can make actually concentric those 2 things. So this concept we are using. And with this concept, actually, we will try to put like 1 by 1. So first we'll put TF1, make this axis. Another element with the same concept, you will put TF2, then check again. It should be concentric. And then 1 by 1, you can actually align those things with the accuracy of, I don't know that I put numbers here. No. So with this concept, actually, you can align your system within 10 arc second or so. So it's a good number, what we were thinking initially. In the end, when you align the things, so as of now, I'm telling just this array. After that, you will also put your AIV optics, align that thing. And then after that, like when your assembly is done, you have to transport this unit to Leiden University, which is the leading project. So where we put this assembly to the Leiden, all subsystems and their subsystem to Leiden, and then they will assemble everything together. So we have to transport those things, and maybe it might be like you have to remove some of the sub-assemblies because of the door dimension and everything. You remove some sub-assemblies, go there, put it again, assemble again, and check the alignment. So this is the last slide from WCU. This is the whole plan, what we are doing now. If you have any question till here, you can ask. Otherwise, I will move to the second part of the talk, which is FOSC instrumentation. Yes. Yeah, good question. So we are using chord mirror, which are aluminum, temperature changes, curvature changes, focus will change, right? So for that purpose, we are using actually linear stage at just after where we put the mask, just after the integrating sphere. So once this temperature changes, you slightly move your object plane, and then focus will remain here. That we are using. That we check like during tolerance analysis, that's a huge range we have. Beam. Yes, yes. Yeah, so we have some numbers. Maybe I need to check those numbers, but those are really loose numbers we have checked during like tolerance analysis. We don't need, no. This thing, like what you asked, like focal plane temperature, that's a critical thing. That's why we have the stage to control that thing. Okay, now I'm moving to FOSC instrumentation for PRL telescope actually, where I just tell in the starting also, I will describe quickly 3 instrument, FOSC, EP, and protocol. So let's start with the FOSC. So what we have in PRL, like two telescope actually. One is a 1.2 meter telescope on the left hand side. On the right hand side, you can see recently we established also 2.5 meter telescope. These are the numbers what we have for the site. Altitude 1680. I think here it is what Davis Thal is 1900 volt. Okay, it's what okay. I was like 2000. Okay, so this is the altitude. Cloud free night, they said 70%. Of course, it will change. And the seeing is roughly 1 arc second. These are the internal telescope, like you can see the telescope structure itself. This is the M4SP design. When I joined PRL, actually, this work already have done. So I actually started working with the AIT phase, like where you have to actually work in the lab and to assemble everything. These are some parameters, like design parameters, that what it does actually, it does imaging and low resolution spectroscopy in optical domain. And resolution we are talking about here around 45, we are talking about here around 500, 1000 and 2000. Those three resolution modes are there. If I quickly explain the concept, we have telescope plane here, then you have collimator section here, some lenses, then you put some broadband filters to do imaging. And here we have actually either you can select grating for the spectroscopy or you can select the mirror for the imaging. Then you have camera section here and then the detector. This is the mechanical design. I will not go through this. Next, like when I joined, from where actually I have started from here. So you receive the lenses, then you have the lenses, you have the mechanical things like parts, and then you just assemble into those cells. And then, of course, you have to check like the first order performance from the lenses, that those are really correct or not. So what we did, like you have, you can make an imaging system, like you have one M4SP lens, then you make an imaging system with off-the-shelf lenses, and then you check the performance in your design as well as in the lab. If those two things are matching, you are good. After that, once we did this verification, we actually starting assembling everything in the barrel. And then this is the collimator section. This is camera section. This is the optical test bench setup. Before starting the full assembly, actually we start on putting the things on the bench and then check, okay, everything is perfect or not. And this is the actual instrument assembly. This is one slide, but the work we did here is actually 5 months work, like starting from assembly and everything. This is the slide where I'm showing the on-sky performance. Of course, when you go to the telescope, you put your instrument on the telescope. Then, of course, you want to see some like first images kind of thing. So we observe this M21 open cluster, and we were just curious, okay, what are the numbers we are achieving, what we have calculated, and what we are achieving. So we just check imaging as well as different modes of low resolution spectroscopy. And these are the numbers what we were getting. V magnitude, around 16 magnitude. In 40-second integration of time, we are getting SNR of around 7.3. And it is actually nearby what we have simulated before. For spectroscopy, I can give one example for R500 mode, which is this one. We are getting SNR of around 40, integration time of 10 minutes, and we are checking this is TCRB, which have the magnitude of around 30. So those are good numbers, and we have characterized everything. I'm not showing all the results, but these are the numbers we are achieving, and those are within the limit what we expected. Now, after this, of course, you have to also characterize your instrument in different elevations for different wavelengths and for different magnitudes. What we choose, M-dwarf, as I said, it was not very specific science. It was just like you grab the spectra and you try to fit with the models and you get some parameters. So what we did actually, you have this black spectra, which is our M4SP spectra. This red one is synthetic spectra. We try to fit chi-square minimization, simple, and then we get like effective temperature, surface gravity, and spectral type. So that we have done, and it shows like, okay, you can do the spectroscopy with this instrument up to around 13 or 14 magnitude kind of. Now, after M4SP, I was also working on this M4SP EP, where I was really working on the design only, not the AIT things. So here, if we talk about like what are the other instruments for PRL 2.5 meter telescope, The front object camera, 4K CCD is there. You also have like Paras 2, which is 107 or 110 maybe, 1000 resolution. And also there is a discussion going on NISP instrument, which is near infrared imaging polarimeter. Then people thought, okay, you also need some kind of low to medium or moderate resolution spectroscope in visible, because if you see these three specifications, this thing I think is really missing at that time. And people thought, okay, I think we should start designing this as well. Then what kind of science you can do with this particular instrument? You can observe like novae, supernovae, symbiotic stars, and many more like AGNs. I'm not putting all those things here. And another requirement was this symbiotic system, that you should be able to do some flickering observation kind of thing, which really needs like in 1 second, you have at least 10 images. So this kind of mode was also required for this instrument. And we also thought, okay, if we are doing the science for 15,000 resolution, you just put some module for the polarimetry also, so that you can do actually the spectropolarimetry. What kind of science can be done? You can see, like one example, this is the symbiotic system, and this is actually the intensity for the spectroscopy. You can see there are two spectra actually. One is dotted one is a solid one. In intensity, you cannot see much variation, but if you do the spectropolarimetry, it shows like there are changes, which means there is asymmetry in the system, which is basically changing with time. So those kind of study can be done with this instrument also. This is spectropolarimetry mode. This one, this is angle. This is, yes, yeah, okay. No, this is like a full instrument in one, and you can choose either of these modes. So you can do like either spectropolarimetry, you can do other things like low resolution spectroscopy or simple spectroscopy. So this is a single instrument where you have different modes. We are talking about here, not here, right? Those two things you are talking. Okay, I was thinking like you are talking about different modes. So those are, I guess, for different port are there. See, so this camera is there. This Paras 2, they have recently working on the characterization. This NISP is actually not there. They are working on assembly and everything. So this may be after 2 years, it will be there. FOSC EP also, it's procuring phase, and it will be like, I think within 2 years or so, it will be complete. Okay, so some kind of basic what you need to do the polarization. Of course, maybe you are already aware that you need some Stokes parameter I, Q, U, and V. I will not talk about because this will be used for the circular polarization. So if you need I, Q, and U, you need this S0, S90, 45, 135, which are 4 different directions of your vector polarization vector. And if you want to measure that thing, you will need 2 elements actually. One is Wollaston prism, which you can, in one shot, you can get like S0 as S90. You need another element also, half-wave plate, if you want to measure this S45 and S135. After that, if you want to do the high resolution, you cannot use the normal gating, which are first order gratings. You need some special gating, what we called Eshell gratings. There's no much difference between normal and Eshell. There's only difference of this blaze angle. Too technical, but if you change your blaze angle, you can work in different orders. So if you want to do the higher resolution, you have to move the higher orders, which means you have to change your grating, basically the blaze angle. And the problem, like if you move to the higher orders, the orders are stacked on top of each other. So you need another grating which can really sort those orders. After this, you know that those elements are required in your system. So this is the final design, optical design, what I finished in my PhD actually. So this is the telescope focal plane, then the collimator section. This is your low resolution arm. If you want to do the spectroscopy or imaging, you can actually put your mirror here and you can fold light into this system. If you want to do the spectropolarimetry, you just remove this mirror somewhere else. And then this is your polarimetric arm, and this is actually your spectrograph arm. These are some parameters. If you are interested, I can tell you the numbers. The important number is like resolution, what we are hitting is 15,000, actually more than that for some wavelength reasons. And another important number is this, the separation between O ray and E ray, because this is more important. When you see the actual spectrum, these O ray and E ray actually can mixed up, and you can't get anything. So we have this 20 pixel separation, which means up to 2 arcsecond we are good. There is no crosstalk between those two rays actually. These are challenges like what we face while we are designing. One of them is Wollaston prism and slit rotation. So what we actually realize, if you just put slit perpendicular to your shell grating group, you will end up on the detector something like this situation, where your slit is actually tilted and the resolution element is actually broader than the slit width, which means you have to rotate everything. Like you don't want to like this, you want to like this, so that you can reduce this factor. For that, you have to rotate this here and this here as well, which means you have to rotate your Wollaston prism, you have to rotate your slit as well. Yeah, so if you see till here, where actually beam separated, we are not using any mirror. Only after that we use. Okay, so this was the FOSC EP. This is the oscillogram, like how it seems on the detector. You have different orders. For each order, you have O ray and E ray spectra. We are using 2 cross disperser, like in 2 settings, you can cover the whole optical range. And as I said, there is no crosstalk between up to 2 arcsecond. And this is the efficiency curve. This is important because if you want to calculate how much polarization accuracy you can achieve, you need efficiency. And what we get is actually polarization of accuracy of 0.15% we can achieve for 9 magnitude star in 1 hour of integration time for each half wave plate position. This is the current status that lenses are being procured, and opto-mechanical design is currently they are developing inside PR. So 1 hour for each half wave plate position. So you need 4. Yes. Okay, so I will quickly finish. I will not go to detail, but just to show that we are also working on protocol, some constraint, optical design, and then we have different sections. One thing is good about this instrument is this line, that we are using completely off-the-shelf components. It means you just go to market, not market like this, but just go in the market and check what are the elements are available. You took those things, assemble everything, and you can have your instrument ready. So with this thing, what we are hitting is the resolution of 7,000, again in 2 settings. And again, we have like separation good, like up to 4 arcsecond, we are good. This is the opto-mechanical design, not by me, but PR engineers are developing those things. And this is the accuracy we are hitting. In 30-minute exposure time, for each half wave plate position, you can get 0.15% because of the resolution we have degraded. This is the current status. It's already on the telescope. People are using this thing. And I think I have done here. This is the contribution. I already told you what I'm working on. And yeah, this is, of course, the last picture. People want to see, like, if you are working in big consortium, even like in PRL, we have this thing, Modit. And yeah, this is like system engineer there, mechanical engineer. I was, if you can see me, and this was electronic engineer. Here you have like a group in the University of Cologne. And this is the consortium meeting picture, like where we, every 6 months, you have to report, okay, what kind of work is going on. If you change something, you have to update them as well. So this is the one. So yeah, here I stop, and thank you for listening carefully. Yeah, if you have questions, you can ask. Which instrument? ELT. 39-meter telescope. No, it's very specific science programs are there. Survey mode, you can think of 2 meters, sometimes 4 meters. Yeah, nowadays, of course, you move to 4 meter. Yeah. So here we have like 1 meter also, and like you can actually think of a survey mode here. This kind of instrument, people are even fighting to get a time. So, yes. So yeah, it will not be in survey. So. Mm-hmm. 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 Wavefront. No, we are not correcting anything. We are within the limit. What was the constraint, and we are below that limit. Mm-hmm. Yeah, no, we are querying. I'm not presenting here. So we have done this thermal analysis, and it shows basically if you change that temperature, at least for operational range, we are talking about only 0 to 15 degrees Celsius. In that range, there is changes, but maybe I can show you later also. While I was compiling everything, there are 3-4 parameters. In one parameter is quasi-static parameter, which take care of that range. So you change the temperature, you have the turbulences, that comes into that category. And in that category, we are also contributing that thing. Even with those numbers, we are good. Yeah. GH band, huh? No, it's not two wave bands. It's it works in GH band. Like there are two modes. Either you can use your guide stars, which like laser sources from the telescope, or you can choose the actual stars. So actual star can be chosen in those wave band. That was the reason. Yeah. So with the JWST, of course, the diameter is 6 meter, I think. 6 meter. So 6 meter, then even you hit the diffraction limited, you will be getting like 1/6 of that. Yes. So you cannot go like what I showed you, like exoplanet thing. So you cannot hit those super warm Earth. This is the basic difference. Yeah. Mm-hmm. Yes. Mm-hmm. Before. Yes. So you see, we inject till here, and then you have coronal section here actually. We block light here, and then it enters into the IFU thing, which is like the slicer, and then other slicer. No, we are not deciding according to the source actually. It is back calculated from the detector constraint. Yes. Yeah. 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 Mm-hmm. Yeah. We are not using fiber, not the consortium. It's not using fiber. Basically, there's a slicer. So you have 0.6 by 0.9 arc second. Even within that, we have 28 slices. It's really tiny. It's 28 slices are there. So people are trying, like if you go to like nebulae planet and then the circumstellar disk, it will be really useful. Input size of 28 slices out of this 0.9 arc second. 0.9 by 28. Yes. this for each field here. नहीं मिलेगा 40 मीटर है ना मिलेगा हाँ I have somewhere because if not. Yeah. So the velocity is here and MIT is here. So sensitivity is around number. No, this number. 10 to minus 20. It's really good. Yeah. We cannot resolve by this. Yes. Yes. You mean by the IFU, the study of the star itself? Yes, people are doing. Yeah. Yes. I had one picture, maybe not in these slides, but people are actually try to do that thing. But because the focus is somewhere else for this instrument, it's basically for the nebulae and all those kind of things. That's why. Yeah. Yeah, thank you. Should I close this session? Someone was online or not? Not. Okay. Thanks. This was mine. Yeah, yes, this was mine. And no. This one, yes. Sorry. It got actually gone out. So. Okay. So you have to be careful, huh? Like in FOSC PL1. This is around like this much, 500 millimeter, 50 centimeter kind of thing. These are very compact. Yes. Do you also like this temperature?